programming models, and we provide an API to help with this as well, will use the term for all to say run all the iterations in parallel. And the meaning of for all is exactly what we had earlier, finish for async. You can logically think of creating a separate task for each iteration and doing a finish when the for all is done. So in that way, you can take any loop and convert it to a parallel loop if it's legal to do so, where all iterations can run independently just by changing it to for all. Now, it turns out that in certain cases, such as vector add, you can express this more elegantly using Java streams, because what you can do is you can generate a closed range say 0 to n minus 1. That gives you a stream of integers from 0 to n minus 1. You can then convert it to a parallel stream by putting a dot parallel operator in between. And then you can do a for each where you perform the computation for each iteration of the for each. And this can be done even more elegantly if you have one return array, like in vector addition, there's only one array being returned, because then instead of this, what you can do is you can convert it to an array where each array element is just the sum of bi plus c sub I. And now instead of having a for each computation that's doing some work, you're generating an array, and then A will need to be assigned this expression. But the key thing is that the parallel operator will enable parallelism, as we had seen earlier. However, when we look at parallel loops in general, it may not be the case that they only have one return value. You may have a loop where you have, say, another array being computed, which is the difference of bi minus ci. And once you have multiple output arrays, like in this for loop, it becomes inconvenient to use streams. So what we will do in this module is use the for all notation for parallel loops and explore the range of algorithms we can create using for all and parallelism. Now that we've learned about parallel loops and the for all construct, let's see how we can apply it to a very common linear algebra algorithm, and that's called matrix multiplication. So the idea behind multiplication of two dense matrices is that, let's say you have two matrices A and B that you want to multiply into a result C. An element Cij of the result matrix is the inner product of row I and column J. Row I of array matrix A and column J of matrix B. And that can be expressed mathematically as a summation k going from 0 to n minus 1 of aik times bkj. Now, our interest is in running this computation in parallel. It's very important to support linear algebra packages that solve a number of important problems in practice. And in fact, this is the kind of computation that's even used to measure the speed of the fastest computers in the world. If you look for a popular website called Top 500, you'll see that the underlying benchmark is really a variation of matrix multiply. So how will we convert this first to sequential code? And we'll go for a simple algorithm here, not a complicated one like Strasson's. So what we could do is say we can iterate through I and j, and we'll write these more high-level for loops. So we've got a two-dimensional space for I and j. And what we want to do is we want to compute for a given I and j the element Cij. So what we could do is we could assign Cij to 0 and then add a new loop k that iterates to 0 to n minus 1 as well, and accumulates the inner product by doing aik times bkj. So this is pretty much a direct translation of the math formula into sequential code. Now, from the viewpoint of parallelism, let's think about which loops can run in parallel. For the I and j loops, we see that each element of a matrix C can be computed independently. So we can very conveniently actually say, instead of a sequential for, we can have a for all. And this works in general across multiple dimensions. It's saying that all n squared iterations for I and j can all be run independently. So what about the k loop? Can we run it in parallel? Well, there's an issue over there, because if you imagine all these k iterations running in parallel for the same Cij, each k iteration can read and write the same Cij, and that would lead to a data race, as we've discussed earlier. So we have to keep this k loop as sequential. So what we've seen is that very commonly used and important dense matrix computation like matrix multiply can be expressed in sequential loops directly from the math formula. And once you have the sequential loops, you can identify which loops could be converted to parallel loops in the form of for all. And here there is abundant parallelism with order of n square parallelism for an n cubed computation. So this gives you a very simple example to work with, and we look at more examples in the exercises that accompany this module. Let us now do a deeper dive into for all loops with a very simple example. Suppose we had a for all that looked like this, I going from 0 to n minus 1, and inside the for all we did some lookup of a string s based on I, and then we printed hello with the string s, and then we print bye with the string s. Now let's think about how these print statements could appear in a parallel execution of this program. It is going to be non-deterministic. Different executions might end up printing these strings in different order. For example, you could have, let's say, hello 2, if the strings, let's say, are the English words for the indices. So maybe 2 could come from I equals 2. We could have a hello from 0, and the order can vary from run to run. We could have a goodbye from 2. We could have hello from 1, a goodbye from 1, and then finally a bye from 0. So there are many possible orderings. The only constraint over here is that the hello and goodbye for the same number should be in order. So we have hello 2 followed by bye 2, hello 0 followed by bye 0, and hello 1 followed by bye 1. Otherwise, any permutation would be okay. But let's say we wanted to add a constraint. We wanted to make sure that all the hellos were printed before any of the goodbyes. How could we change our code to do that? Well, one thing we could consider is to put another for all over here for the second print statement. But the problem over there is if you have a second for all, this lookup value will need to be communicated from the first loop to the second loop, or the lookup needs to be performed again. And in general, you may have more expensive computations that you don't want to repeat. So instead, we have this construct called a barrier over here. And what the barrier does is ensures that when you have a parallel loop, all the iterations reach the barrier, and none of them go past the barrier till all the iterations have reached that point. And so when you do have a barrier and consider the print statements that could be possible, you can have any permutation of hellos, but you cannot have a single bye be printed before all the hellos have completed. So we may end up in this case having hello 2, hello 0, but we could not have a goodbye from 2 until the hello from 1 has completed. Then we have hello 1, and then it's not a print statement, but this is the point at which you reach the barrier operation. And once all iterations have reached the barrier, then all of them can pass the barrier. So that's exactly why it's called a barrier. It's a waiting point where you wait for all the iterations to assemble before going to what's called the next phase. In fact, people refer to this as phase 0 and phase 1 and so on. And you can have large numbers of phases. So after the barrier, you can have the goodbyes, and they can be in any order. They needn't be in the same order as the hellos. You can have a bye from 2, a bye from 0, and a bye from 1. So we've now seen how we can extend the for all construct with a new capability called a barrier, which is a special kind of synchronization primitive that can be inserted inside a for all to separate phases, sequential phases that each for all iteration undergoes. And it's a coordination point so that no iteration goes to the next phase until all the iterations have completed the previous phase. You'll find this notion of barriers in all kinds of parallel programming models for GPUs, whether it's CUDA or OpenCL, for distributed memory machines, something like MPI. And in fact, we have many forms of barriers available for Java programs. And we will see a more interesting example using the barrier construct next. Let us now look at a very simple example of a stencil computation, while in practice there are many more complicated examples like this. So the problem is as follows. Let's say we want to solve this recurrence 2 with some boundary conditions where you have, let's say, x sub 0 is 0, x sub n is 1, and we want to do this for 0 less than I less than n. So I going from 1 to n minus 1. So we're really trying to figure out, in this case, an iterative averaging example. How can we compute xi such that it's the average of its neighboring elements? And this is in a one-dimensional array. As I mentioned earlier, we have stencil computations that work on much larger arrays, multidimensional, that essentially follow this pattern. So you can think about it and maybe figure out that the solution is quite easy to work out in practice. If we had n equal to 10, then for I going from 0 to 10, you'd have 0 and 1 at the boundary, and the intermediate values would be 0.1, 0.2, and so on to 0.8, 0.9. And if you take a look, you can quickly convince yourself that each element is indeed the average of its two neighboring elements. Now the question is, instead of solving this in our head, how could we write a computer program to come up with this answer? Well, the usual approach that's taken is to have two arrays, and this is in an algorithm that's referred to as Jacobi relaxation. Let's say you have an old value of the array x, and you have a new value of the array x. And in every iteration, you're going to compute new x, the ith element, as the average of the I minus 1 and the I plus 1 elements of old x. Notice the way I've drawn it. We can see that all these elements of new x can be computed in parallel with each other. And when we are done, we are going to swap the pointers so that what was earlier new x becomes old x, and what was earlier old x can now accumulate the values for the next phase. And the idea is if we keep repeating this computation, we will eventually converge to the answer that we figured out analytically. The reason the computation is important is in real world problems, we do not have an analytical solution, and we need this computation to obtain the answer. So how would we write code to do this computation? Well, we have an outer iteration loop, which we can consider kind of like a time step loop. And that will go from 1 to some number of time steps. And then for each time step, we're going to do one of these parallel steps. So we can have a for all for I that goes from 1 to n minus 1 and does the update with new x I equal to, and I'll just write the average of old x I minus 1 and old x I plus 1. And when we're done with the for all, we have to swap the pointers. So this is fine. We can go through a large number of steps and each time have a for all. But there is an inherent inefficiency in this approach because each for all has n minus 1 tasks, and that gets multiplied by the number of time steps. So we have n steps times n minus 1, a quadratic number of tasks being created. Now, it turns out this is exactly the scenario for which barriers can help you generate more efficient code. And to do that, what you have to do is, and it's very interesting, you have to move the for all loop outside where you go. You have the for all loop outside, and then within each iteration of the for all, within each parallel task I, you do the sequential loop. You have the sequential loop, and then within the sequential loop, you can perform this update for I, which is the new x sub I equals average of old x I minus 1 and old x I plus 1. And now here's the challenge. You want to swap the pointers and go to the next time step. But before going to the next time step, you have to make sure that all the i's have completed computing the new x average, because we're going to swap the pointers and start overwriting what was old x in the next phase. And if we don't have this coordination, then we'll end up with some data race condition. And this, as you can guess, is perfectly suited to a barrier operation. So we can insert a barrier over here. This is also referred to as a next operation, which is an indication that the for all loop has to move to its next phase after the barrier. And with this, we ensure that all the i's which are running in parallel for a given time step complete their updates, wait on the barrier, swap pointers, and then go to the next round of updates. So what we've seen is that barriers can be used not just to separate two phases like we saw earlier with hello and goodbye. They can be embedded in sequential computations like for loops and while loops, and help coordinate across tasks. Now, the big advantage of doing this approach is we only have n minus 1 tasks created. That's it. We do have the number of barrier operations is still n minus 1 times n steps barrier operations. but the number of tasks is much fewer, and this is a much better trade-off in practice because creating tasks is much more expensive than a barrier operation which just involves coordination among tasks that have already been created. So now you've seen a more interesting example using barriers, and it is indeed reflective of a lot of real-world computations.